Welcome back to The Explainer. So, let's just jump right in, shall we? Today we're unpacking what is easily one of the most powerful concepts in AI right now, how LLM fine-tuning actually works. If you've been wondering how big organizations take these massive off-the-shelf foundation models and morph them into laser-focused tools that just absolutely get their specific business needs, well, you are in exactly the right place. To set the stage here, we gotta ask, why do these genius AI models sometimes completely faceplant on specific tasks? Think of your standard foundation model like a brilliant, world-class general practice doctor. I mean, they know a little bit about absolutely everything, right? They can diagnose a cold in 2 seconds. But what happens if you hand that same doctor a scalpel and ask them to perform pediatric cardiology? Yeah, it's going to be a struggle. AI models are the exact same way. Out of the box, they are incredible generalists, but they really need some help to become specialists.
And honestly, that is exactly where fine-tuning comes into play. By definition, fine-tuning is just the process of continuing the training of a pre-trained model on a smaller, much more task-specific dataset. The whole goal is to boost its performance in one particular domain. The absolutely crucial takeaway here, we are not spending millions of dollars building a model from scratch. No way. We're just taking our generalist doctor, sending them off to a specialized fellowship, and building on their massive existing knowledge base.
Here's a quick look at the roadmap for today. We're hitting the core fine-tuning concept, whether you should fine-tune or not, methods from full to PEFT, the step-by-step process, and finally, best practices and pitfalls.
All right, part 1, the fine-tuning concept, taking things from generalist to specialist. The core mechanics of this are actually elegantly simple when you look at the input-output flow. You basically start on the left with a base LLM. Think of a huge open-source model you just grab online. Then you feed it your custom domain-specific dataset. And what do you get on the other side? A highly tailored, specialized, fine-tuned LLM. But why go through the hassle? Why does this matter? Because a domain-adapted model will consistently crush a generic model on tasks within that specific domain. When you fine-tune, you are essentially baking in knowledge that the general internet just doesn't possess. We're talking about niche corporate jargon, super specific medical reasoning, or even just nailing a brand's exact tone of voice. A specialized model handles all of that vastly better than a standard, out-of-the-box algorithm ever could.
Moving on to part 2, to fine-tune or not, choosing the right adaptation tool.
Okay. Before we get too deep, we have to compare prompt engineering with fine-tuning, because fine-tuning isn't always the answer, right? Prompt engineering is basically just telling the model what you want right there in the input box. It's super fast, it's cheap, and it is entirely reversible. But you're heavily constrained by what the model already knows. Fine-tuning, though, that physically updates the model's parameters. It enables really deep behavioral changes and true domain-specific knowledge. But yeah, it definitely costs a lot more in terms of compute and setup time.
Which brings us to the massive industry debate everyone's always arguing about: fine-tuning versus RAG, or Retrieval Augmented Generation. Let's make this super simple. Here's the golden rule. RAG is your go-to for dynamic, constantly changing facts, like if you're searching a live company database. Fine-tuning is what you want for embedding a new linguistic style, a behavior, or a specific task structure. So RAG updates the knowledge context, while fine-tuning alters the fundamental behavior. And the best part? You can totally just use them together. It's not an either-or situation.
All right, section 3, methods from full to PEFT. Let's look at the math behind the magic here.
So the traditional old-school approach is full fine-tuning. This updates literally every single weight across the entire architecture of the model. And as you can probably guess, this gives you the absolute deepest behavioral change possible. But man, the downside? It demands immense GPU memory and a budget-busting amount of compute. For your standard enterprise task, full fine-tuning is just incredibly resource-intensive. Honestly, it's usually overkill. So how are we solving this compute nightmare? Enter LoRA, or low-rank adaptation. This is an absolute game-changer. It falls under the umbrella of PEFT, Parameter Efficient Fine-Tuning. Instead of trying to update billions of parameters, LoRA cleverly freezes the original model weights entirely. It only trains 2 much smaller approximation matrices. So it essentially learns the changes it needs to make without ever touching the massive original architecture. And the efficiency gains we're talking about here are just staggering. A LoRA adapter is typically just a single-digit percentage of the original LLM size. We're talking megabytes, not gigabytes. That saves an absolutely massive amount of memory.
It makes it entirely possible to train incredibly powerful models without needing an entire warehouse full of servers.
But wait, practitioners are pushing the boundaries even further to train these giant models on single GPUs. Take QLoRa, for example. Engineers quantize the base model all the way down to 4-bit precision before they even apply LoRa, which drastically shrinks the memory footprint. Or they might use half fine-tuning, where they freeze exactly half the parameters. This creates this perfect balance, letting the model learn new skills while rigorously protecting the foundational knowledge it already has.
Moving into Section 4, the step-by-step process. Let's break down the 7-stage life cycle.
Phase 1 is data and setup. And look, it all starts with dataset preparation, where you're curating these high-quality prompt-response pairs. I seriously cannot stress this enough. Preparing and cleaning your data is the most time-consuming and hands-down the most critical step for success. Garbage in, garbage out, right? If your data is messy, your model is going to be messy. After that, you've got model initialization, picking the perfect base model, and your training setup, where you define those tricky hyperparameters, like nailing the exact learning rate so you don't accidentally overwrite the model's brain.
Then we roll right into Phase 2, train and deploy. This is where we actually run the fine-tuning, updating the weights via full training or PFT. We evaluate the heck out of it using automated benchmarks and real human review. And finally, deployment and monitoring. Now this is where PFT really shows off. Because LoRa adapters are so tiny, you can load your massive base model into memory just one time, and then literally hot swap these little adapters in and out for different tasks on the fly. It's amazing.
Finally, Section 5, Best Practices and Pitfalls, how to actually safeguard your model.
Okay, I really want to drill this golden rule into your head right now. A smaller dataset of high-quality examples will consistently outperform a larger dataset filled with noisy data. When you're dealing with instruction datasets, quality beats quantity every single time. Honestly, a few hundred flawlessly crafted examples are infinitely more valuable than 10,000 messy thrown together ones.
But, okay, that does lead us to a slightly terrifying question. What actually happens if your model learns its new specialty a little too well and literally forgets how to speak English? I know it sounds crazy, but this is a very real phenomenon. It's called catastrophic forgetting. Yeah, when you aggressively fine-tune a model on a super narrow task, it can completely obliterate the general intelligence it built up during its original pre-training. To prevent this catastrophic forgetting, engineers have to rely on some pretty strict technical safeguards. They limit the trainable parameters using techniques like LoRa. They use extremely low learning rates, we're talking in the range of 10 to the negative 5th power here, and they have to ensure that their custom dataset, even though it's specialized, still remains highly diverse.
You also have to be on high alert for overfitting. This is what happens when your model just perfectly memorizes your training data. It's like a student just memorizing an old practice test, right? When you put it out into the real world with brand new, unseen production data, it fails miserably. It'll start generating these highly confident, completely incorrect outputs. To preserve the model's ability to actually generalize, you've got to use validation datasets and employ early stopping, basically pulling the plug on training the exact moment your validation loss starts to rise.
Which brings us to the end of our explainer today and leaves us with one final, pretty exciting question. Are you ready to build a specialist AI that perfectly understands your business? We've seen exactly how fine-tuning bridges that massive gap between generic, out-of-the-box text generators and highly precise, domain-adapted enterprise tools. By just starting with a focused pilot project and leveraging super efficient methods like LoRa, you can unlock some serious value. Thanks so much for learning with me today, and hey, I challenge you to go see what kind of specialized intelligence you can build next.